Awesome. Good morning, everybody. How is everybody today? Tired? Yeah, I hear that. You should try having a 2-week-old in the house. Students never get to complain about being tired again. Just kidding. You can complain. But complaining is not going to do you any good, so, might as well save the effort. So, for those of you who arrived, congratulations, you got the message that lectures are going to be in person again. I received some updates from the university regarding the strike and what's going to happen with things if the strike happens. Apparently, the university has judged it inappropriate that lectures be held online during the strike so as to avoid the picket line. So I have been given explicit instruction that during the strike action, if such a thing materializes, which it's likely to, we have to come into campus to class anyway, apparently. This is, this has come from on high, so, yes. Question?
Are you still allowed to record the things and put it on YouTube?
Well, yeah,
Okay.
Yeah, I'm definitely going to still record things. Yeah, I'm still going to record the lectures and put them up to YouTube because, even if it's an empty room, I hope like one person shows up so they can hold the camera, but aside from that, yeah. So, any questions about anything at all before we get started?
When do we get back our midterm?
The midterms, we'll be returning them in class on Wednesday. I'll be able to collect them all Monday and Tuesday, and then Wednesday we'll have the great feeding frenzy. After class, not using class time for it. Any other questions? Okie dokie. So, I'd kind of like to go through depth first search for you guys on the blackboard because that's, useful. Even though we covered it last class, I think. How many people would like a go-through of depth first search on the blackboard? The majority of you. Presumably this is why you actually came to class. So, good. Need a random graph. Random graph. Random graph. That's probably enough. 1, 2, 3, 4, 5, 6, 7, 8. All right. Yep, that's a graph. Somebody call out a starting position. Huh?
4.
1 makes sense as a starting position, even though 0 is technically before it. All right, so this will be our starting position. All right, so the depth first search. All right, the first thing that we have to do, we should have the vertices saved in some kind of data structure so that we can read that data structure to obtain the adjacent vertices of any vertex of the graph, right? The order in which these things are stored inside of the adjacency array, that will dictate the order in which they get searched by depth first search. This is in contrast to versions of the depth first search that you may have seen over trees or other more regular data structures. On a tree, it's very easy to say, oh, just search the left branch first. Whenever you're anywhere, search the left branch first, then the right branch, then everything's fine. Graphs are more general data structures than trees. A tree is very regular. It always has a fixed number of children arranged hierarchically. Everything's fine. Everything's good. Graphs are a bit of a mess. With a graph, there's no telling how many adjacent vertices any particular vertex might have, right? The number of connected adjacent vertices is arbitrary. It could be all of the other nodes in the graph, it could be none of the other nodes in the graph, or anywhere in between. So that's one very important thing to sort of have sink in about graphs, is there's no implied hierarchy in them, right? We don't talk about nodes as being parents and children anymore. We talk about them as being adjacent or connected, right? Insert joke about communism. So, if we were to form an adjacency array for this particular one, we would of course have 0, 1, 2, 3, 4, and 5, all of our vertices. These would point to lists. So, 0, what's it adjacent to?
4, 3, 2.
4, 3, 2. 4, 3, 2. I'm just going to use commas. You're going to have to deal with it. What's 1 adjacent to? 5, 3. What's 2 adjacent to?
3, 0.
3 and 0. What's 3 adjacent to? 5. Yes. 5, 1, 2, 0. 4. 5 and 0, and 5. 1, 3, and 4. Very good. So, with the depth first search, the branch that you followed to, because you're following one branch down to its conclusion, and then you backtrack and follow other branches, right? With the depth first search on a graph, because the ordering of the adjacent vertexes inside of the adjacency lists, because that's arbitrary, that also means that the branch that you're following during depth first search, we're going to be talking about breadth first search later, the branch that you follow during depth first search is also arbitrary, right? So, we're going to see, perhaps we've already seen, once you perform depth first search on a graph, what you end up with is a tree. Basically, it's one way of generating a tree from a graph. It removes all the cycles, right? There are going to be several correct answers for any particular graph, right? There are going to be several correct trees which can be generated from any particular graph, depending on the order in which these numbers appear in the adjacency array. Does that make sense? Right? Because if you're searching this node first, it's going to look one way. If you search this node first, it'll look another way. Right? So, okay, good, fine. Enough about that. So, in addition, we have a marked array. Right? The marked array keeps track of which nodes have been searched and which ones have not. Right? So, the purpose of this is to ensure that we're not retracing old ground. Again, not so much of an issue with a tree, because trees are acyclic, right? But if you have a graph which might be cyclic, you don't know if it is or not, right? Any cycle in the graph, without marking where you've been, any cycle in the graph will be traversed ad infinitum. You will get stuck in an infinite loop if you try to depth first search down a loop, right? So, the purpose of the marked array, in part at least, is to prevent the depth first search from turning into an infinite loop whenever it hits an actual loop in the graph. Make sense? Good? So far so good? Thumbs up? Thumbs up. Okay, good. So, beginning at 1, we look it up, we see that our first number is 5, so we search 5. We have visited 1, and now we have visited 5. Right? Next, we look up 5's adjacent vertexes. So it's 1, 3, and 4. 1 has already been visited because it's been marked. 3, however, is the first one that we hit, which is not marked. So we recursively depth first search on 3. So our next go is to 3. Good. 3 is now checked off. Now, we take a look at 3's adjacent non-marked vertices, in this case 2 and 0. Looking it up, we've got 2 occurring first, right? So, we now search 2. Boom. Good. We're making progress. We take a look at 2's non-visited adjacent vertexes. We see that we have 0. We don't even have to look it up. Well, I mean, this is how we would tell what this, like, in the computer, this diagram doesn't exist, right? In the computer, this is the representation of this diagram, right? So, really, honestly, this is just for the purpose of human visualization. All of the operations are actually occurring between these two data structures here, right? Am I making sense? Right? Okay, so when we have to like try not to fall into the trap of, okay, like by obvious inspection of this graph, right, we can see that 0 is the only non-visited adjacent vertex of 2, right? But you still have to like think like the computer and go through the data structure, right? Because the question is, if there's a mismatch between what this guy says and what this guy says, this is the correct one, right? Because that is modeling this. This is the primary data. Even though in this particular example, I drew the graph first and derived this from it, you know. Anyway, anyway, 0, we take a look at 2, we look up 0, we've got 0, all right? So we visit 0, right? 0 has now been visited, and we have, do you mind if I modify the graph? Just because this is not a good example, because it's just gonna be a line. But so I'm gonna destroy this link right here using the awesome power of my supreme authority as instructor. There we go. And 0 also means to not connect to 4 anymore. There we go. All right. Because now we can actually see backtracking, right? So if we were to like view how the tree has been developing this whole time, right? We started at 1, we go to 5, we go to 3, we go to 2, we go to 0, right? So we're at 0. We note both 3 and 2 have been visited. So we pop back up to the previous level, right? We exit this recursive call and resume this one. Just keep going through 2's adjacency list. 2's adjacency list happens to not have anything in it that's unmarked. So we pop back up, we pop back up. We note that 5 does have an item which has not been visited yet, right? So we visit it. Boom. The graph has this one tiny little branch, just like that. There we go. Depth first search. Question?
In the previous example, wouldn't the resulting tree be a linked list?
Yeah, yeah, it would, yeah. If I had not busted that last, if I had not broken this link, then yes, it would have been a linked list, essentially, or at least a very similar to a linked list in structure. Yes. So you may ask yourself the question, why would we bother with all of this, right? The depth first search algorithm, one of its very important uses is to determine whether or not two vertices are connected, right? So if we imagine, just for sake of argument, we had two more vertices here, just sort of hanging off, unconnected to the rest of the graph, we would have two more entries here, 6 and 7. We would have 6 is connected to 7, 7 is connected to 6. We would have gone through this entire algorithm without ever visiting 6 or 7 because there is, of course, no edge connecting them to the rest of the graph by definition of them being unconnected. There's no path to follow to them, right? So when the depth first search concludes, we have all of those nodes which are connected to the starting node marked, and those which are not connected to it unmarked. Although you can't tell like what group these things are in, right, relative to each other. Like you could have another one, 8, that's just hanging off by itself, and it would look like they were all in one group if you were not thinking about it too clearly and just thinking marked means it's in one group and unmarked means it's in another group. It's like, yeah, unmarked means it's in any possible other group, right? Does that make sense? Thumbs up? Okay, good. Cool. So, any questions about the, yes?
Can this be used as a pathfinding algorithm?
As a pathfinding algorithm? Yes. Although, generally speaking, when you're writing pathfinding algorithms, what you typically want is a shortest path finding algorithm, right? The most basic approach to shortest path finding algorithms is the breadth first search, which is the cousin of this one. So we'll we'll get there. Okay? Question? Yeah.
I was wondering how the actual search for connected would work, because you said that it would mark for this one group. You can either tell that if it's marked or unmarked, and everything that's unmarked could be part of any other group. So, for example, let's say 3 and 2. How do you check if they're connected?
Union
Very good
find?
question. So the question is, if we were given two nodes, how would we turn this into something more like the connected function we had in union find, which is to say, just how do I do a Boolean on this, right? How do I get the Boolean? Is it connected or isn't it? So the example you gave was 1 and 3, right? So that's easy because we've already done the search for 1, right? So connected x, y, right, is just depth first search taking x as the source and then marked at y, return marked at y equals check mark in pseudocode. Does that make sense? Yes?
Do you need to perform on the depth first search every single time? Or can, for example, if 3 is connected to 1, and 5 is also connected to 1, then 5 should be connected to 3. So could you use that? If you already performed the depth first search, can you use that, or do you have to do it again?
Not unless the graph changes, right? If the graph remains unchanged between calls to the depth first search, then obviously, yeah, you could just like, keep an auxiliary linked list of all of these numbers, and that would give you all of the, everything in a group. And if connected was any two members of that group, you could just like cache the results, and that would speed you up considerably. Of course, you have to delete all of that cache information as soon as even one new edge is added, right? Because one new edge might connect you to nodes that previously you weren't connected to, right? But to be completely honest, if you're this concerned about connectedness, you should probably be using union find anyways. The whole thing about like depth first search on general graphs is that a graph is capable of way, way, way more different types of algorithms and forms of analysis than just union find, right? That being said, it is also good to know that we can perform a connectedness analysis on a graph, like on a general graph. Make sense? Awesome. Question?
So this only works when the keys are integers, right?
Say that again?
This only works if the keys are integers.
Nope. This could work. So you would need a symbol table in between, right? So these the keys on these nodes do not necessarily have to be integers, but if they're not integers, you would need a symbol table that translates between whatever type of key they are and integers, so that you can look them up. Does that make sense?
Yeah. So just all those integers in that array.
Yeah. Yeah. So let's, if we were, let's just say, for the sake of the argument, you had a graph that was like A, B, C, right? You would need some kind of symbol table in addition to all of that, so that anytime you were trying to look up, like, basically it will map whatever your keys are to index position inside of the adjacency array. But once you've had that, then everything's fine. Cool. It is more simple for the purposes of demonstration, however, to just use integers. Any other questions? These are excellent questions so far. Okay. So, good. Yep. I'm going to assume that me having done one on the board is better than that. So let's talk about a few properties of the depth first search before we move on to breadth first search. So, oh my goodness, I'm actually out. I don't have any. Where's that beam? Where's that aluminum? I need a pointing stick. There it is. All right. There we go. There. So, proposition. The amount of time that depth first search takes to mark all vertices is proportional to the sum of the degree of all of the vertices in the graph. Remember that degree, the degree of a vertex, is the number of other vertexes which are adjacent to it. This should make a certain degree of intuitive sense right off the bat, as when we go through, when we go through our connections to check to see whether they're marked or not, the number of checks we have to perform is not proportional to the number of vertices. It's proportional to the number of times those vertices have been referenced inside the adjacency graph, right? So, we are, in this case, proportional to the number of numbers stored here, not the number of numbers representing vertexes. Does that make sense? Good. So, proof. First, we prove that the algorithm marks all vertices connected to the source and no others. This should be like very obvious, right? You just make a very simple inductive argument, right? Your source, right, is, we probably consider it connected to itself. That would be useful. We say all things connected by a connection to the thing, to the group of nodes that we're already connected to. You know, if you keep doing that, eventually you'll get the node you want. But let's see what this is. So suppose we have some unmarked vertex x connected to s. Since s itself is marked, any path from s to x must have at least one edge from the set of marked vertices to the set of unmarked vertices. Say v gets connected to x, right? So these up here, the white nodes here are the set of marked vertices, the gray ones are the set of unmarked vertices. So the algorithm would have discovered x after having marked v, so no such edge can exist, right? So yeah. So this is basically a proof by contradiction here, right? What we're saying is that if we assume that, so let's imagine that we have some vertex which is unconnected, right? Like 6, for example. We want to show that 6 is not reachable by depth first search, right? So we hypothesize the existence of such a connection, right? So we hypothesize the existence of it, and then we prove that it can't happen, and that's proof by contradiction. So the reason that it can't happen basically it's contradicting contradicting the definition of connectedness, right? So if we have it's a very complicated way of saying that if they're unconnected, there's no edge, right? So if there's no edge, right, then the edge that would connect this thing to the rest of it, in order for it to be found by depth first search, can't exist. Therefore, the thing's unconnected. It's, again, one of these times when mathematicians make things that are simple entirely too difficult. So, any questions before we move on to breadth first search? Okay, so shortest path algorithms are when you're talking about graph algorithms, shortest path algorithms sort of occupy the same position within the field of algorithms research that sorting does over an array. It's like a very important algorithm which is performed frequently, which has a number of approaches, which we're going to study in turn, and if you don't study shortest path algorithms, you really haven't studied graphs, right? So it depends on what you mean by shortest as well, right? So in the context of the unweighted, undirected graph, we are considering distance to be just the number of links that we have to travel through to get from point A to point B, right? Once we introduce weights to our graph, we're going to be interested in minimizing the, minimizing the weight of the edges that we have to travel through to get to the point that we want to get to. But at the moment, everything's reasonably simple. We don't have weights to consider yet. Or, if you prefer to complicate things needlessly, we are dealing with weighted graphs. It's just that all of the weights on all of the edges happen to be 1. Just like we're technically dealing with bidirectional, we're dealing with a directed graph where each edge is bidirectional, right? That's also true. So basically, shortest path algorithms are extremely important. Yeah, how many people have ever played a video game? All right. How many people have played a video game where an enemy character has moved from one point on the screen to another point on the screen? All right. How many people, okay, if the character actually has to, it's like a top-down and has to make decisions about where it's going, it's using something close to a depth-first search, or a breadth-first search. It's using a shortest path algorithm, right, to find you, and the skeleton is coming for you, right, and it's anyway, it's applicable to games which are modelable as graphs, which is some of them and not others. But anyway, shortest path algorithms are very important. Let's move on. So, the depth-first search does not give us really anything to work with if we're trying to find what the shortest path from one point to another is. So we perform a different algorithm known as the breadth-first search. So I'm just going to might as well use the same graph, right? Sure. Am I getting this right? Might not be. 0 is 2 and 3. Right. 0 is 2 and 3. 1 is 5 and 2. Good? Yep. Yeah. Okay. I think that's good. All right. So, let's imagine that we are performing the breadth-first search and trying to find out if someone give me a random node in the big group.
5.
5? All right, I heard 5. So we're trying to find out if 5 and 6, what the distance between them is. All right? So, good. So, the manner in which we perform the breadth-first search, beginning with our source node, we look up the adjacent nodes, and we put them into a FIFO queue. All right? The difference, in some sense, the difference between a breadth-first search and a depth-first search is the manner of queue that you're putting the nodes in for processing, right? In the case of a depth-first search, you are putting these things into a stack so that the most recently added things to the stack are popped and processed first. It just so happens that that stack can be, you can use the system call stack implicitly as that stack, right? But in the case of a breadth first search, we are putting the nodes that we wish to process into a FIFO queue. So the first ones that go in are the first ones that go out. For each node, we are still marking the nodes that we visit in the same way that we do for depth first search. And that's mostly it. So, let's have our FIFO. So in this case, we're starting with 5, and we wish to determine the shortest path to 6. So 5 goes into our FIFO queue first. We process 5, looking up, see it's 1, 3, and 4. So into our queue, we put 1, 3, and 4, right? And then we mark 5 as having been visited, right? Next. So effectively, it does this. Next, we take a look at 1, right? 1 has now been visited. We will take a look. We've got 5 and 3. 5 and 3. 1 gets crossed off, right? Both of those have been processed, or will have been processed by the time we get there, but that's somewhat immaterial. We then take a look at 3, right? 3 has now been visited. We take a look at these guys here, so we add them to the queue, right? Three has been processed. 4 has nothing remaining connected, but we can put it in there anyway. 4 has been processed, right? 5 has been processed. 3 has been processed. 5 has been processed. 1 has been processed. 2 has not. It's got nothing unique, but we can say we visited it now. 0 has nothing unique, but we can say we visited it now. And then by the time you've gone through the entire FIFO queue, you have fully explored the tree, or you've fully explored the graph. So, how that ends up looking here and 4, 2, and 0. So, one very important property of the tree which is generated via the breadth first search is that if you examine any of these levels of the tree, the height of that level, or the depth of that level, if you take the root as being 0, gives you the distance of that node to the source node, right? Now, in this case, since we're looking for 6, we might look through our marked array, notice that 6 was not marked, and then, throw an exception or something, because the thing we're looking for wasn't found. But you can see how if we were looking for 0, for instance, all we would have to do is return the, the depth of 0 in that tree, and there we've found the thing we're looking for. Does that make sense? So let's talk about this example on the board for a moment then. this is the same graph that we were doing the depth first search on previously. You'll notice that, you didn't believe me when I said undirected graphs were simply directed graphs where each node, where each one is bidirectional, but there you have it, my friends, there you have it. So, in this case, trace of the breadth first search to find all paths from 0. So in this case, we're just simply wanting to construct that tree. We're not like looking for a connectedness or anything like that. So, we start with 0 in the queue. We add 2, 1, and 5 to the queue, which are the connected things, according to the adjacency matrix. 1, 2, and 5 have 0 written to them in the edge 2 array. So, in the same way that under the union find algorithm, we had this interesting way of representing a graph where we had an array representing all of the vertexes, and the value placed in each address in that array points you to its parent, right? What the edge 2 array is doing is it's creating that very self-same parent, parent tree representation, just at the same time as we're processing the algorithm. So when 0 gets processed, we know each of its children because we look them up in the adjacency graph. We then take each of those children and write 0 in for them inside of the edge 2 array, right? If we do this, if we do this consistently, by the time we're finished, we will have the same kind of tree representation encoded in an array that we had in union find. Does that make sense? I think the only difference here is that the root isn't pointing to itself, but so it goes. Any questions? All right. So, step 1. We start at 0. 0 is in the queue. We mark 0. We then put 2, 1, and 5 into the queue. Write 2, 1, and 5 as zeros, and you can see they're doing it all at once, as opposed to me who did it one at a time here, but either way. So, in this version, 2, 1, and 5 are immediately marked off in one step, rather than, waiting and marking them as you travel to them, which I suppose is a bit more efficient. So, having done that, we then proceed according to whichever is the next one in the queue. So we add 3 and 4, which are nodes which are not marked in the marked array, right? 3 and 4 get added to the queue. They also get marked off, and because it's 2 that you're getting to them from, it's 2 that you put into the edge 2 array. Does that make sense? Okay, good. And then, of course, we have all of these things left in the queue. Since they've all been visited already, and there's nothing that they point to which has not been visited, you simply perform that check to make sure that they're empty, knock them off the list, and then you have produced a breadth first search. Make sense? Once again, the specific ordering of the tree is dependent on the order in which values appear in the adjacency array, right? In this particular example, it's basically arbitrary whether we started at 2 or started at 5, right? Now, it just so happened that in this particular instance, it would have been, you know, actually, that's kind of an interesting little tangent. What if we had searched on 5 instead of 2? Would we still have gotten the same distance from the starting node for, you know, 4, for example, right? So, does anybody need this? Can I erase it? You good? Okay, good. So, let's imagine, and I know class is going to be over quickly, so I'll try to make this quick. Yep, okay. So, so in this in the version that we have up here, we start at 0, we search these 3 guys, right? And we then search this guy, that 2 yields 3 and 4. What if we had searched 5 first, right? So let's imagine that we go for 5 first. 5 finds 3. Remember, things are being kept in a queue. So in this case, it would be something like 5, 2, 1. Instead of in the previous case, it's 2, 5, 2, 1, 5, right? So we process that, we find 3, 3 gets added, right? Cross that off. 1 has nothing. 2 finds 4. 4 gets added. Then you cross them off. So it doesn't change the result of what how long is the shortest path to this node. That result remains the same. All that does is it pops it into the tree becomes slightly differently configured. That's all. Instead of having 2 children, 2 ends up with 1, and 5 ends up with the child that 2 no longer has, right? But the depth in that search tree does not change, and therefore we have basically an isomorphism, right? We have 2 different trees that will yield the same result for all of the nodes in those trees. Does that make sense? Question?
If we have 3 nodes, we start from the middle and all starting from 8, that's different depths. You simply have 3 nodes there, and they connect together. But if we start from the middle, that's 1 level down, finish. But if we're starting from the edge, that's
the distance to any particular node in the graph is going to be different depending on which node you choose to start off with, right? Like you could imagine, if you had a graph that looks like this, right? Something like that. Let me just add some things here. If you select this as your starting node, then all of the other nodes are accessible in one step. But if you select this as your starting node, then this node can only be accessed in 2 steps, right? So yeah, it's natural for the depth, for the distance to change depending on where you start and stop inside of the graph. Make sense? Any other questions?
So
Yes.
if a vertex is already marked, you don't put it in the QI.
Yes. Yeah. Sorry about my earlier example. Should have done the slides one first. Any questions? Yes?
So where do you keep track of what's the shortest path? Like if you have a function shortest path x, y, how would that look like?
So once you have generated the edge 2, right, it's the number of times you have to perform a lookup in this to find the root node. And the root node needs to be distinguished by either having a null or pointing to itself or some other manner of being able to distinguish it. But yeah, to find, distance to 3, you find 3 yields 2, so that's 1. 2 yields 0, that's 2. 0 is its own root, so the answer is 2. Make sense? Any other questions? Okay, good. See you on Wednesday.